Chapter 7 is about right triangles, and we know that whenever we deal with the right triangle, we deal with Pythagorean theorems. So lessons 7.1 and 7.2 I've combined to talk about Pythagorean theorem and its converse. The Pythagorean theorem. In a right triangle, the square of the length of the hypotenuse, which we know is the longest side and the side across from the right angle, is equal to the sum of the squares of the lengths of the legs. So in this case, we have c squared is equal to a squared plus b squared. Though you can plug into the Pythagorean theorem to find either the hypotenuse or a leg, if you think about it, there's a shortcut to the process. So what I'm going to do is I'm going to solve the literal equation in order to cover the two possibilities of these shortcuts. The hypotenuse squared is equal to the leg squared plus the leg squared. So if I want to find the hypotenuse, all I have to do is get rid of that square. We know that we do that by taking the square root of both sides, and what I get is that the hypotenuse is equal to the square root of the sum of the two legs squared. Now notice that square root will get rid of the square on the hypotenuse, but it does not get rid of the square on the legs because of that plus sign there. That works completely differently. So remember, you have to keep that squares under the square root for the legs. The other possibility is when we're actually looking for a leg rather than the hypotenuse. So in order to find a leg, we need to move one of those over to the other side. So we'll subtract leg squared from both sides. So I get the hypotenuse squared minus a leg squared is equal to the other leg squared. Now when I square root, I get this situation. So look at this. When you're looking for the hypotenuse, which we know is the longest side, you must add the two sides squared together and take the square root. Whereas when we're looking for a leg, which is a shorter side, we will subtract the leg we know from the hypotenuse. Of course, they're squares, and then take the square root. Let's look at a couple of examples of doing this. Find the missing side of the right triangle. In this case, we're looking for the hypotenuse. So I know what I'm going to do is I'm going to take the square root of the legs squared and added together. So x is going to be equal to the square root of 6 squared plus 8 squared, and we get 10. In this case, I actually know the hypotenuse. It's 26. And I know one leg is 10. I'm looking for the other. So when I'm looking for a shorter side, the side that is not the longest, then I'm going to simply do the square root of 26 squared minus 10 squared, which comes out to be 24. We can use this to find the altitude or height of an isosceles triangle, and therefore the area of the triangle. To find the altitude of an isosceles triangle with side lengths 16 feet, 17 feet, and 17 feet. The two sides being equal means that it is an isosceles triangle. To find the altitude, remember an altitude goes from a vertex to the opposite side, forming a right angle. When it's an isosceles triangle, it just so happens to also be a median. It splits that opposite side into equal parts. So what I have here is actually one isosceles triangle that once I drop that altitude in there, I have two right triangles. So we can find the height, since it is one of the shorter sides, by doing 17 squared minus 8 squared and find out that our height is 15. Remember, to find the area of a triangle, we use the formula area equals 1/2 the base times the height. So I now know my height. Half of the base, the whole base was 16, and half of that is 8. So 1/2 of 16 times 15 gives me 120 square units for that area. There is another type of shortcut, which is making use of what is known as Pythagorean triples. There are certain numbers that when plugged in to be the side of the triangle always gives you that c squared equal a squared plus b squared. Any set of three positive integers which satisfies the Pythagorean theorem is called a Pythagorean triple. Common Pythagorean triples and some of their multiples: 3, 4, 5. A 3, 4, 5 triangle is one of the most useful triangles that you will run across, and is used all the time in the construction field, in any type of landscaping, any type of interior design. Those people make use of the idea that a 3, 4, 5 triangle is always a right triangle all the time. Notice that I can get 6, 8, 10 simply by multiplying each of them by 2. I can get 9, 12, 15 by multiplying the 3, 4, and 5 by 3, and so on. So anything 3x, 4x, and 5x, where x is simply some number, will end up being a Pythagorean triple. 5, 12, and 13 also works. 13 squared is 169. 5 squared is 25. 12 squared is 144, and if we add those together, we get 169. Therefore, it's a Pythagorean triple. And the same way as the 3, 4, 5, we have multiples that also work. The 8, 15, 17 works, and so does 7, 24, 25. These, you can remember the base ones and use those as shortcuts. The ones that you'll see most often is a 3, 4, 5, but these other ones can be helpful also. The most common triples are in the bold. The others are a result of multiplying each integer in a bold-faced triple by the same factor. Remembering the common triples can help you solve many problems much more easily. Find the length of the hypotenuse of the right triangle. Now, of course, we could just use Pythagorean theorem, but if we happen to notice that a 5, 12, 13 is a Pythagorean triple, and 10 is simply 5 times 2, and 24 is simply 12 times 2, so the other side has to be 13 times 2, or 26. Like I say, you can use Pythagorean theorem, just plug into it and get that if you don't recognize that it is a triple. The converse of Pythagorean theorem basically just says that if the square of the length of the longest side is equal to the sum of the squares of the other two sides, then we know it's a right triangle. So what this is doing is saying that we're going in the opposite direction. If we know it's a right triangle, then this has to be true. If this is true, then we know it's a right triangle. So how do we determine if it is a right triangle or not? Well, we plug in. Does 3 times the square root of 34, that whole quantity squared, equal to 9 squared plus 15 squared? They both come out to be 306, so yes, it does. So we know that we have a right angle that is across from the longest side. So that is a right triangle. What about this one? Well, we'll check it also. This 26 squared equal to 22 squared plus 14 squared. We find out that it is not, so we cannot say that we have a right triangle. So here's a guided practice. You need to pause the video, try to work these out, and then see whether or not you got it right. Number 1 is yes. We need to know whether 4 times square root of 3 is the largest side or not, but we can plug in to see if 8 squared is equal to 4 squared plus 4 times the square root of 3 squared. This is 64. This is 16. This is 16 times 3, which is 48. And yes, we get 64 equals 64. No, this one does not work. 14 squared is not equal to 10 squared plus 11 squared. And yes, this one does work. The square root of 61 squared is equal to 5 squared plus 6 squared. And you could plug that in and see. Theorem 7.3 says if the square of the length of the longest side of a triangle is less than the sum of the squares, then the triangle is an acute triangle. Now, if you'll think about that, that should make sense. if c squared is equal to a squared plus b squared, then this has to be 90. But if c squared is less than a squared plus b squared, then this must not be opened up quite enough to be 90. And so what we end up with is it's an acute triangle because it's less than 90 degrees. We have another theorem that says that if the c squared is bigger than the a squared plus b squared, then that must be bigger than a 90-degree angle. Therefore, it's obtuse. So can segments with length 4.3, 5.2, 6.1 form a triangle? Remember, that's from the last chapter. And if so, would the triangle be acute, right, or obtuse? Well, how are we going to check that? First thing we're going to need to do is use the triangle inequality theorem to see if they work. 4.3 plus 5.2 is 9.5, and that is bigger than the third side, which is 6.1. 4.3 plus 6.1 is 10.4, which is bigger than 5.2 or the third side. And the 5.2 plus the 6.1 is 11.3, and that is bigger than the third side when you pair those up. So yeah, we got a triangle there. The side lengths can form that triangle. Now, is it right, acute, or obtuse? Well, to do that, we're going to plug into Pythagorean Theorem. C squared compared with a squared plus b squared. When we work that out, we see that c squared actually ends up to be less than a squared plus b squared, since the longest side is across from the largest angle, and it's less than what is required by Pythagorean theorem, then that is an acute angle. And if the largest angle is an acute angle, then all three of them have to be an acute angle. Acute. Show that the segment lengths 3, 4, and 6 can form a triangle and classify it as acute, right, or obtuse. So remember what we have to do. This is for you to try, but now that you've tried it, let's see. 3 plus 4 is 7, which is greater than 6, so that works. 3 plus 6 is 9, which is greater than 4, so that works. And 4 plus 6 is 10, which is greater than 3, so that works. So we do have a triangle, can form a triangle. Now, is it obtuse, right, or obtuse? Well, let's see. 6 squared compared to 3 squared plus 4 squared. 6 squared is 36, 3 squared is 9, plus 4 squared is 16. 36 is greater than 25, and therefore this is obtuse, because c squared is greater than a squared plus b squared. So we're looking to compare those, and we find out that it's greater. So it does work, and it is obtuse.